Welcome to our continuing discussion on the flow in a pipe. Okay. We had first solved the momentum balance equation for the steady flow to get a parabolic profile for the flow in a pipe, and I had shown you that we get the equation for the friction factor for a laminar flow in a pipe. I had discussed qualitatively some features of transition to turbulence and some features of turbulent flows. Okay. Turbulent flows are in general difficult to describe. So, the simple techniques that we have developed here will in general not be applicable to a turbulent flow. Despite that, there are some gross or some broad features of the turbulent flow that can be deduced just from simple analysis and dimensional arguments. Okay. So, I had shown you that for a turbulent flow, the bulk of the flow, there are velocity fluctuations in all directions. There are eddy velocity fluctuations, correlated parcels of fluid that are in correlated motion, and so therefore, a turbulent flow is inherently unsteady and it is inherently three dimensional. The velocity fluctuations are not only in the flow direction, they occur in all three directions. And these velocity fluctuations or these correlated parcels of fluid, they transfer momentum far more efficiently than the transport due to molecular diffusion. And for that reason, the transport coefficients in a turbulent flow turn out to be much higher than the transport coefficients due to molecular diffusion. And for that reason, the velocity profile is approximately flat here, because the transport takes place very fast. Okay. As you go close to the wall, the turbulent velocity fluctuations have to decrease to 0, okay, because the fluid velocity has to be equal to 0 at the wall. Therefore, as you go close to the wall, the turbulent velocity fluctuations have to decrease to 0. The length scale of these fluctuations also has to decrease to 0, because a region in correlated motion cannot have a size larger than the distance from the wall, because the velocity has to be 0 at the wall. And because of that, the diffusivity due to the turbulent fluctuations decreases to 0 as you go close to the wall, okay, because both the magnitude of the velocities decrease and the length scale decreases. And therefore, close to the wall you have a region called the viscous sublayer, within which the flow is dominated by viscosity. Okay. You do not have turbulent diffusions. In this region, the characteristic velocity scale is obtained from the wall shear stress, because you have the region is a very thin region and you can consider the shear stress to be approximately a constant across that region. That constant is equal to the wall shear stress. From that, we managed to get a friction velocity and a length scale, okay, a wall unit based upon the kinematic viscosity and the friction velocity at the wall. Okay. So, close to the wall, when you express the velocity in terms of the friction velocity and the distance from the wall in wall units, you just get a linear profile ux plus is equal to y plus. Okay. Since the wall shear stress is much higher than what it would have been for a laminar flow, okay, I said that the turbulent diffusivity is much higher. So, the rate of transport to the wall is much higher than what it would have been for a laminar flow. Therefore, the slope near the wall is higher than what it would have been for a laminar flow. Okay. That is the reason that close to the wall, okay, the gradient of the velocity is higher than what you would get for an equivalent laminar flow. And therefore, the shear stress is also higher, because the shear stress is the viscosity times the velocity gradient. And beyond this viscous sublayer, you have a region called the logarithmic layer, where the velocity profile is logarithmic in the distance from the wall. Then beyond that, there is the bulk of the flow. I had said we will start a discussion on oscillatory flows in this lecture. Okay. I had briefly told you how to get the solution for the startup of the flow in a pipe. Okay. And in this lecture, we will talk about an oscillatory flow. Okay. So, I have a pipe. And I have a pressure difference across this pipe, okay, across a length L, and this pressure difference is an oscillatory function, okay, delta p by L, okay, as a function of time. If I plot that, okay, if I plot this pressure difference as a function of time, it is an oscillating function. Okay. So, I will approximate delta p by L as some function cos or some constant k times cos of omega t, okay, where this time period is 2 pi by omega. Okay. Omega is the frequency of the oscillation. Okay. So, I am approximating this pressure gradient as a sinusoidal pressure gradient. Okay. I am approximating this pressure gradient as a sinusoidal pressure gradient with one frequency. Okay. It turns out that you can solve the problem for any general shape, okay, because any waveform we know can be expressed as the sum of sine functions. Okay. So, if you had any arbitrary periodic waveform, okay, if you had any arbitrary periodic waveform, okay, this periodic waveform can always be written as the sum of sine functions of different frequencies. Okay. So, if I solve it for one particular sine function, okay, I can get a solution for arbitrary periodic waveforms by just adding up the solutions due to the different sine functions that comprise this periodic waveform, okay, by just adding up the sine functions that comprise this periodic waveform. Okay. I will come back and discuss that a little later. So, the point I am making is that considering a sinusoidal profile is not a loss of generality. Okay. Any waveform can be expressed in terms of sinusoidal profiles. Okay. So, for now we will consider a sinusoidal profile. Okay. Momentum conservation equation for this case. So, this is x, this is r, okay. Rho dux by dt is equal to mu by r d by dr minus dp by dx. Okay. Minus k cos omega t. So, that is the momentum conservation equation, okay. And I have the boundary conditions, okay, at r is equal to capital R, ux is equal to 0, and at r is equal to 0, dux by dr is equal to 0. The symmetry condition there, because there is no physical boundary at the location r is equal to 0. So, how do we solve this equation? Okay. It helps first to scale the equation. Okay. I can scale the equation, the radial distance r star is equal to r by capital R. Okay. And what about the frequency, the time scale? Okay. I already know that omega t is dimensionless. I already know that omega t is dimensionless. Therefore, I can scale, define a scaled time t star is equal to omega t. Okay. What do I scale the velocity by? Okay. It is not yet clear at the present juncture. What would I scale the velocity by? Okay. So, if I do it in this fashion, if I scale omega t as t star, the equation that I will get is rho omega partial ux by partial t is equal to mu by r square. I have two derivatives with respect to r in this equation. So, I will get mu by r square 1 by r star d by dr star of minus k cos t star. Okay. Because omega t was equal to t star. So, you just get k cos t star over here. Okay. Now, I can divide this entire equation by this pressure gradient k, okay, because delta p by L, the amplitude of that pressure gradient is k. Okay, so I can divide throughout by k. Okay. So I'll get rho omega by k partial ux. Okay, I should put a t star there. It's equal to mu by r square k minus cos of t star. Okay. So once I have divided throughout by k, right, this term here is dimensionless. That means that all the other terms in the equation are also dimensionless, okay, because in an equation all terms have to have the same dimension. Okay. So if one term is dimensionless, it means that all the other terms are also dimensionless. Okay. So I can scale the velocity now in two ways, in one of two ways. Okay. I can scale the velocity now in one of two ways. The first way is to scale it by the viscous scale here. Okay. The first way is to scale it by the viscous scale. The other way is to scale it by the inertial scale here. Okay. The other way is to scale it by the inertial scale. Okay. Which one do we choose? That of course depends upon whether in the problem the ratio of inertia to viscosity is large or small. Okay. And we do not yet know what is the ratio of inertia to viscosity. So for the moment we will just scale it by the viscous scale. Okay. So I will define ux star is equal to ux mu by r square k. Okay. I will define ux star is equal to ux mu by r square k, which means that ux is equal to r square k ux star by mu. Okay. Put that into the conservation equation. Okay. So the first term I get rho omega by k, okay, into r square k by mu, okay, into partial ux star by partial t star. Okay. Since I have scaled by the viscous scale, on the right side I will just get 1 by r d by dr of r dux by dr minus cos of t. Okay. And in this first term here k cancels out. So therefore this becomes rho omega r square by mu. Okay, that is the coefficient. Okay. This is a Reynolds number based upon the frequency of oscillations and the radius of the pipe. Okay. This is a Reynolds number based upon the frequency of oscillations and the radius of the pipe. Okay. So this is the conservation equation, which contains just one dimensionless parameter, okay, a Reynolds number based upon the frequency of oscillations and the radius of the pipe. Okay. Now, how do we solve this equation? Okay. So the equation is of the form Re omega partial ux by partial t is equal to 1 by r d by dr of r partial ux by partial r minus cos of t. Okay. This is a partial differential equation. It contains functions of both, it is a function of both time and radius. It is an inhomogeneous partial differential equation. Okay. It is an oscillatory, so the velocity exactly repeats itself after each cycle. Okay. Now how do we solve this equation? The simplest way to solve this equation, okay, if you recall, I had my equation was of the form, okay, Re omega partial ux by partial t is equal to okay, minus cos of t star. Okay. This cos t, okay, it is the real part of e power I t. Okay. It is the real part of this function e power I t, because e power I t is cos t plus I sin t. Okay. Because e power I t is cos t plus I sin t. So, this is the real part of e power I t. Okay. So, what I can do instead is to solve the equation, another equation solve another equation. Since the inhomogeneous term in this equation is the real part of the inhomogeneous term in this equation, okay, since the inhomogeneous term in the momentum equation is the real part of the inhomogeneous term of this modified equation, and the equation is linear, okay, and the equation is linear, what that means is that the solution, okay, u x star will be equal to the real part of this modified equation w, okay, will be the real part of the solution for this modified equation. Okay. Note that this is a linear equation, okay, this is a linear equation. The real part of the inhomogeneous term for this, okay, for this modified equation, the real part of this inhomogeneous term is the inhomogeneous term for the momentum equation. So, the real part of the solution of this w for this modified equation will be the solution for u x. Okay. So, that is always guaranteed in the theory of complex variables. Okay. I should note here that I is equal to square root of minus 1, okay, and e power I t can be written as cos t plus I sin t. Okay. Therefore, the real part of e power I t is just the cos function, which was the inhomogeneous term here. Okay. So, the strategy for solving is as follows. I will solve this equation for w. I will get a function, a solution for w, which will be some function of r and t. Because the inhomogeneous term is complex, the solution w will also be complex. Once I found the solution for w, that complex function, if I take the real part of that complex function, I will get the solution for u x. Okay. So, that is the idea. Okay. The real part of the solution for w will turn out to be the solution for u x. Okay. And this is always guaranteed if you have a linear equation. Okay. Okay. So, rather than writing it in terms of w, I will just write in terms of u x itself. Okay. I will just write the equation in terms of u x itself. Okay. Partial u x by partial t is equal to 1 by r star minus e power I t star, okay, with the implicit understanding that because e power I t is a complex function, the solution for u x will also be a complex function. The real physical velocity profile will be the real part of this complex function, okay, with that understanding. Okay. So, on this basis, this is the equation we have to solve. I have to solve the equation with the inhomogeneous term becoming e power I t. Okay. How do I solve this? Since the inhomogeneous term is an exponential, I can write the velocity u x also in terms of exponentials. Okay. I can write u x star, okay, is equal to some function, okay, some function v of r star e power I t star. Okay. And if I put that in to this equation, okay, if I put it into this equation, you will find that this factor of e power I t star is common in all terms, okay, and therefore it will cancel out. Okay. So, therefore, dux by dt is equal to I v of r e power I t. Okay. Therefore, I will get r e omega into I v of r e power I t is equal to, now when I take the derivative with respect to r, I get only derivatives of v. Okay. Therefore, I will get e power I t coming out 1 by r d by dr of r dv by dr minus e power I t. And this factor of e power I t cancels out on both sides. Okay. And I will get r e omega I v of r is equal to 1 by r d by dr of r dv by dr minus 1. Okay. So, if the forcing is of the form e power I t and the equation is linear, okay, if the forcing is of the form e power I t and the equation is linear, then the response also have to have the same frequency. Okay. The response also has to have the same frequency. There may be a phase shift, okay, but the frequency has to be the same, because the forcing is at one particular frequency and the equation is linear equation with that forcing, then the response also has to have that same frequency. And for that reason, we were able to write down the velocity in this form here. Okay. And now this equation that results, okay, it is only a function of r. There is no time dependence in this equation. Okay. And that is the basic simplification here. Okay. I had said originally that we are solving partial differential equations. They are functions of space and functions of time. And there is no standard method for solving partial differential equations. We have to use physical insight into to reduce them to ordinary differential equations. We had seen two such procedures. One was the similarity solution, where there was a deficit of dimensions, and therefore we were able to reduce the equation to an ordinary differential equation by identifying the similarity variable as z by root alpha t, okay, or r by root alpha t, okay, as the case may be. Okay. The second was separation of variables, where we wrote it in terms of the product of a function of position and a function of time, and use separation of variables to get those solutions individually, add them up, and then determine the coefficients from the inhomogeneous term. This is the third such method. In the case of oscillatory flows, you know that if the forcing is at one particular frequency, the response also has to be at that same frequency. And therefore, if I express the time dependence, okay, in this particular case, the velocity is a function of r and t. The velocity is a function of position and time. If I express that time dependence as a sinusoidal time dependence and I put it back into the equation, I get an equation that is only in the spatial coordinate. It is an ordinary differential equation. Okay. So, I can simplify this equation a little bit. Okay. What I get is that d square v by, okay, so let me do it in steps. Okay. I can take the inhomogeneous term, okay, to the left side. I will get 1 is equal to 1 by r d by dr of r dv by dr, okay, minus I r e omega v. Okay. Or my equation becomes 1 is equal to d square v by dr square plus 1 by r dv by dr minus I r e omega v. This is an inhomogeneous equation. Okay, this is an inhomogeneous equation, linear inhomogeneous equation for the solution V. Okay. So, therefore, I can write the solution V for V as the sum of two parts, the general solution plus the particular solution. Okay. The general solution is the solution of the homogeneous equation. Okay. The general solution is the solution of the homogeneous equation. Okay. The homogeneous equation in this case is the equation with the inhomogeneous term set equal to 0. So, the homogeneous equation is dV d square V minus I R e omega V is equal to 0, and the particular solution is any one solution of this inhomogeneous equation. Okay. It can be any one solution of this inhomogeneous equation. Okay. We will continue this solving this equation in the next lecture. Kindly go through the solution of inhomogeneous linear differential equations, ordinary differential equations. How do you separate it out into a homogeneous solution and a particular integral, and how do you add up the two in order to get the final solution. Okay. So, I will continue the solution of this equation in the next lecture. So far what we have done for this oscillatory flow, we had a partial differential equation, and based upon some physical insight we had reduced it to an ordinary differential equation, a function of the radius r times e power I t. Okay. And we have to find out this complex function of r. So, once I find out the solution for r, I multiply it by e power I t, take the real part, that is going to be the solution for my velocity profile. This I will continue in the next lecture. I will see you then.